Hi, I'm Ying Liang, and today I'll talk to you about the work we did on maintaining a reliable world model using action-aware perceptual anchoring. In order to complete complex tasks, robots need to interact with objects and other agents. But these interactions often cause them to lose sight of surrounding objects, especially for eye-in-hand systems. So it's important for robots to reason about their surroundings to maintain a reliable world model. Object permanence is a fundamental concept which describes the understanding that objects continue to exist even when they are no longer perceived. Psychologists believe that infants develop full object permanence at around 2 years of age. In robotics, object permanence is an important concept with practical benefits. For example, to augment the robot's searching and tracking abilities, or for belief management and perspective taking when engaging with humans. Most recently, Shamsian et al. Addressed this problem by dividing it into 4 parts: visible objects, occluded, contained objects, and carried objects, which is also referred to as invisible displacements and is considered to be the most complex task. They then trained OpNet, a neural model for learning object permanence, which consists of 2 LSTMs to infer the object to track and its exact location. While OpNet outperforms other learned and programmed models, such as the heuristic model, where we track the object which is closest to the last known position, it doesn't outperform them by a big margin. For our work, we believe that relying only on low-level perception is not enough. If you take, for example, this image sequence, there are 2 possibilities. Either the white oil plug is occluded by the hand, so it would not move when the hand moves away, or it is carried, then it would move together with the hand. This means that we require knowledge about the executed action that can help us perform high-level reasoning about the location of the lost object. So for this, we define so-called object attachments, which is a semantic relation that describes the state that 2 objects are physically bound to move together. For example, the oil plug is attached to the hand. In this case, we refer to the plug as the child and the hand as the parent. It is a many-to-one relation, which means that an object can only have one parent, but one parent can have multiple children. We can infer attachment relations from executed agent actions. This means that if we know that a pickup or a screw action has been performed, then we can infer the location of the oil plug even when it's not visible anymore. We propose the action-aware perceptual anchoring model, or AAPA, where we use high-level reasoning with low-level object detection to improve the robot's object permanence capabilities. We consider agent actions to infer attachment relations and track lost objects. For this, we make the following assumptions. The object state changes are observable, which means that objects do not move by themselves, and state changes are caused by agent actions. They are also gradual, which means that objects detected in successive frames have similar attributes. And finally, they are consistent, so objects that exist in the scene will be detected consistently. These assumptions allow us to make reliable inferences on the positions of objects that are no longer detected by the perceptual system, but are physically still present in the scene. Here you can see the end-to-end pipeline of our approach. We take the input from an object detector, which provides us with the perceived bounding boxes of the objects. This input is first fed into the object alignment component, which compensates for camera movements. Then we find the optimal alignment between objects from the previous time step and the newly perceived ones. In the next step, we perform hypothesis reasoning on the object positions, where we decide if they are occluded or out of view. We also use inferred object attachments to track lost objects that have parents. And finally, all objects have a confidence value which is increased or decreased if the objects are detected or not. Symbols in our world model are maintained or discarded depending on the confidence threshold. This threshold can be adjusted according to the reliability of the object detection output. The maintained world model is then used by ICRA, which is a cognitive architecture for modeling human cognition. We infer in symbolic states and relations and the executable agent actions. After action execution, the world state and action information are passed back into AAPA in the subsequent cycle. To evaluate our approach, we performed quantitative experiments on the LA-CATA dataset, which is based on CATA, a dataset for reasoning about object action and interactions in videos. Each video is 10 seconds long and consists of 300 frames and 5 to 15 objects of different shape, size, material, and color. The dataset contains 4 annotated actions, which we consider to be performed by an invisible robotic hand. There are no objects of the same type, none of them go out of view, and there are no camera movements. We benchmark on a snitch localization task using the test data for the 4 object permanent tasks. For evaluation metrics, we use the IOU, which is the intersection over union, as well as the Euclidean distance of the bounding box centers. We compare AAPA to OpNet and a heuristic model and ran experiments using the code provided by the authors. All models receive the same bounding box input, which is either from an object detection model, pre-trained faster RCNN, or a perfect perception, which consists of ground truth relocations of bounding boxes. Using the perfect perception will allow us to compare the model performances without having any detection error being propagated to the model performances. Here you can see the experimental results. AAPA outperforms baseline models by around 12% on carry tasks, as well as using IOU and L2 distance. When using perfect perception, AAPA's performance increases the most, reaching an overall performance of 96%. For more details, please refer to our paper. Here you can see a comparison of OpNet and AAPA, where the blue box shows the ground truth and the yellow box the prediction. Common failure cases for AAPA were as follows: moving in occlusion, bounding box misalignment, and anchoring errors. We integrated AAPA with the cognitive architecture ICRA on the universal robot UR5, which has 6 degrees of freedom. It was also mounted with an Intel RealSense camera for an eye-enhanced system. We received bounding box information from a faster RCNN, which we fine-tuned on the gearbox assembly domain. And we used the cognitive architecture ICRA for world state inference and action execution. Here you can see AAPA's functionalities, where the top right corner shows the bounding box input from the faster RCNN and the bottom right shows the maintained world by AAPA. So as you can see, AAPA maintains the unique IDs for all of the objects, as well as objects that go out of view. Now we will show you the robot completing a collaborative gearbox assembly task in real time. Again, you can see the maintained world model by AAPA on the bottom right. In summary, we propose an action-aware perceptual anchoring model that uses high-level reasoning with low-level object detection to improve the robot's object permanence capabilities for complex tasks. We consider agent actions to infer object attachment relations and to track lost objects. Our rule-based approach can accommodate object detection errors and more complex tasks such as carried objects. And unlike neural models, this allows us to reason about tracking failures and improve our model. The system outperforms other state-of-the-art models on the LA-Cater dataset by about 12% on carried tasks. We integrated APA with the cognitive architecture ICRA on the UR5 robot and demonstrated its use in a real-world application on a collaborative gearbox assembly task. For future work, we will look into using human action recognition and common sense reasoning to infer attachments from human actions involving certain object types, such as screws or container objects. Thank you very much.